Hello and welcome to this revision session which forms part of the GCSE Forces module for GCSE Separate Science, and in today's revision session we're going to look at moments, levers and gears along with pressure. Now in these revision sessions what I'm going to do is I'm going to go through the key concepts of the course in a little less detail than was given in lesson videos, but I'll be going through the concepts a bit slower to discuss what they mean and how they work through. So, what we're going to look at in the first part of this revision session is we're going to look at moments. So, if we consider the following object. The object's fixed to the side at point X. Now, if we place a force downwards on the object, and we always draw the force of an object from the centre of mass of the object in a free body diagram, so we draw it at the centre because that's where we assume all the mass of this particular object is, we'll realise that this object wouldn't actually go straight down because it's being held in position at point X. So this force acts towards the centre of the Earth, it's the weight of the object, but it wouldn't actually cause the object to just go straight down because it's fixed at point X. So, whilst the weight of this object is acting on it due to the force of gravity of the Earth causing it to be pulled down towards the Earth, it would actually rotate. So, we call this fixed point of an object the pivot or the fulcrum. So, like when you screw an object into the wall, that will be acting, where it's screwed into, will be acting as the pivot or the fulcrum. So, point X in this example is the pivot or the fulcrum. Now, whilst this force is acting downwards, in reality, the object's going to rotate because it's being held in position at point X. So that will combine to cause a rotational effect on the object because it's fixed in position. So, the resultant force will cause an object to accelerate by changing its direction, by causing it to rotate. Now, the effect of a force causing a rotation or a turning effect is called the moment of the force. So if a force causes an object to rotate, normally because it's being held in position by at some point of its shape, it will cause a moment or a turning effect. Now we can calculate the size, the actual value of the moment by doing the equation moment equals force times by perpendicular distance from the pivot, where it's fixed, where it is moving around. Now, the perpendicular distance is the distance of a parallel line between where the force acts and the pivot. So it's where the force is acting we call the line of action. So actually that arrow is technically representing the line of action of the force, and obviously between that line of action and the pivot. Now remember, in an exam question, you should always use the perpendicular distance. In some exam questions, they try and trick you by giving you more distances, and you have to select the perpendicular distance in the diagram to put into your equation to work out a value for your moment. Now, if we pop our units in, well, moments are measured in Newton meters because the force is measured in newtons and the perpendicular distance is measured in meters. So we're multiplying newtons by meters to get the units of Newton meters. Now, try not to confuse the units of the moment, Newton meters, and the units of the spring constant, newtons per meter, with each other, because whilst they look similar, they're not the same unit. They are different units. So they're not the same. Now, moments are vectors. Now, vectors are quantities that have a size, a quantity, and a direction. Now, as they're making the object rotate, you can give the direction in which the rotation is acting in. In this example, the rotation is going to be anti-clockwise because it's going the opposite rotation to what a clock would do. So this moment is acting anti-clockwise. It's always best practice with a vector, you always state its direction. Now sometimes you can state the direction with a positive or a negative, but if you can't, you've literally got to state the direction it's acting in. So this equation you've got to memorize for your exams. You've just got to memorize that moment equals force times by perpendicular distance. So let's just recap so far. So the effect of a force which causes an object to rotate is called the moment. Another name for it, which is sometimes given in the real world, such as using in cars and vehicles, is the torque. So that's another name for a moment. The point in which an object rotates about is called the pivot or the fulcrum, and we can calculate a moment with the equation moment equals force times by perpendicular distance. So let's look at an example question. In this particular question, you can see that Fred has a perpendicular distance of 0.5 meters between the pivot and where his force is acting upon. So his distance is 0.5. His force, which is his weight in this example, is 500 newtons acting down. So the moment is 500 times by 0.5, which is 250 newton meters. That would be enough if it was a scalar, but it's not a scalar. It's a vector, so we've got to give the direction. And as you can see, this particular rotation would be going anti-clockwise. Now you can work that out from looking at where the point is fixed and where the force is acting, and then use your intuition of the real world to see that the seesaw is going to go down, so it's going to rotate anti-clockwise. So you can state that with your answer. Now we can get objects to rotate about a pivot, okay, but we can also get objects to balance about a pivot. Now, the principle behind getting an object to balance is called the principle of moments. So you can consider the following when objects are balanced on a pivot. So if you've got two forces on either side of a pivot, they're going to cause the object to rotate, and you're going to have moments, but the moments going to be on either side of the pivot. Now you'll notice in this particular diagram that the moments are acting in opposite ways. So one is causing a rotation clockwise, the other is causing a rotation anti-clockwise. So you'll soon realise that the two effects will cancel each other out. So as a result, if the moments are equal on either side of the pivot, that they'll completely cancel out, so there'll be no rotation one way or the other, so the object will balance. So mathematically, you'd say one moment was a positive and another moment was a negative. You don't have to say which one's which, just that one is a positive, one's a negative. So you get no resultant moment. So as a result, the object would stay balanced. Now, the scientific name for when an object is balanced is we say it's in equilibrium. Now, technically, for it to be truly in equilibrium, not only do the moments have to balance on either side of the pivot, but also the forces acting upwards and the forces acting downwards on the object will also have to balance and equal out as well. So basically, if we just keep it to GCSE physics at this point, if your object's in equilibrium, the moments on either side of the pivot cancel each other. So what we know is that the anti-clockwise moment will equal the clockwise moment. So then you can use your sums to work out the values. So you'd say that the force times by the distance causing the anti-clockwise moment will equal the force times by distance causing the clockwise moment. Now, it tends to be that in an examination question, you'd be given 3 out of the 4 terms and then asked to work out the 4th term based on this. Now, just to clarify, if there's more than one moment on one side of a pivot, you've got to work out the moments individually on that side of the pivot and then add them in total. So in this example, because there is force 2 and force 3 on the right-hand side of the pivot, you'd have to do force 2 times by distance 2, then do force 3 times by distance 3, add the two moments together, and that's the total clockwise moment. So just be aware of that. So how do you solve questions involving the principles of moments? So step 1, work out the moment on the side of the pivot you've given the force and the distance for. Step 2, state that the moments on either side of the pivots must be the same, and then work out the force or distance value, as you'll know what the moment is on that side of the pivot and you'll know the other value from the question. So an example question is, so you don't know what force 1 is, but you do know what distance 1 is, you do know what force 2 is, and you do know what distance 2 is. And you know that if the object is balanced, that therefore the moments on either side, the clockwise and anti-clockwise moments, must equal each other. So what you do is you fully write out the question. Force 1 times by distance 1 equals force 2 times by distance 2. You then place your values in your equation. Now, it's very important you place your values in first before you rearrange, because you actually get a mark on your examination for identifying the correct values and how they link to the equation. So actually, whilst I know it's very tempting just to rearrange it first, it's actually more beneficial marks-wise to put the values in first. So let's say F1 times by 6 equals 10 times by 4. So F1 times by 6 equals 40. Let's do some rearrangement. Force 1 equals 40 over 6, so force 1 equals 6.7 newtons. Now always give your value with units and also give it to the correct number of significant figures. You'll look in the question and all the values are given to 2 significant figures, so you give your answer to 2 significant figures. Now let's do the last thing, which is really important, and that's the common sense check. Now we know that the distance times by the force must be equal on both sides. So you've got to think to yourself that if you've got a bigger distance on the left hand side compared to the right hand side, to get an equal moment, that the force will have to be lower, and that is what takes place, so it does make sense. Let's look at another question. So again, what do? You put your equation written out, you put your values into your equation, you then can simplify and rearrange where appropriate. So we then get our answer, which we find to be 2.0 meters. So we give our answer with the correct number of significant figures and with the unit. And then the last thing that you always do in these situations is a common sense check. So again, let's have a look. So we know that distance times by force on either side must give the same number. So 3 times by 10 equals something times by 15. So if the force has gotten bigger on the left hand side, the distance is going to be smaller because to get the same number, and it is, so it makes sense. Now, a spanner is an example of an object having a moment exerted on it. So the moment is caused by a force being applied from a distance from the pivot. So in this example, the pivot is actually the nut that's being turned, because that's what's actually fixed. Now, this is actually a very, very simple mechanical system. Now, this system will require a lot of force or effort to make it work, which is why it can be sometimes very, very difficult to tighten or loosen a screw. So humans devised a way to make this task easier. So we use something called a lever. Now, a lever is a device used to transmit a moment in a system and then alter the forces at different parts of the system. So let's just define a few things. So firstly, the effort force is the force that the human will put in to the particular system. Now what will happen is, in this particular lever system, a human puts an effort force in, and then a much larger force is then exerted by the lever to actually carry out the job that's required to do, which is useful because it allows humans to put in quite a low force, but then actually get a high force out, allowing the human to actually do something that they couldn't ordinarily do. So levers work on the following principles: that the moment produced at all parts of the lever is the same, but the force can change at different parts of the lever. Now that actually makes sense, because whilst we say things like energy and momentum have to be conserved, forces don't have to be conserved in a system. So the moment has to be constant, but the force can change to ensure the moment is constant. So you can change the output force to be different from the effort force, so you can get more out than you put in. So what happens is the lever increases the output force compared to the effort force, so we get a better mechanical force acting on the object, so it makes it easier to do work. So we call systems that do this a force multiplier. So just remember, what's the equation for a moment? Well, moment equals force times by distance. So if you've got to keep the moment the same, what you would do to get a bigger force is to decrease the distance, because if the distance is a smaller number, the force is a bigger number to get to the same moment. So look at this particular example. So the human has quite a high distance away from the pivot. So as a result, they only need to exert a small force to get a moment of a particular size, but then past that, the bottle top opener is a small distance away from the pivot. So if the human establishes a moment for the bottle opener to have that same moment in the system, because its distance to the pivot is smaller, the force produced by the bottle opener will be larger, so therefore the output force is bigger than the effort force. So as a result, it takes the top off the bottle, which a human couldn't do by themselves with the force they would apply normally without the device. So we've gained what we call a mechanical advantage. Another example is scissors. So you put your hands into the loops of the scissors, and these loops are quite a distance away from the pivot, the screw of the scissors. So when you exert a force, because the distance is quite large comparatively, it will produce a moment of a certain size. So for the other side, for the blades to produce that same moment, which must be the case in any lever, because it's a small distance from the pivot, the force exerted by the blades must be large to get that same value of a moment, which is why the cutting force of a scissors is very high and can cut objects. So our small effort force is turned into a large output force. We've gained a mechanical advantage. So that's why it's actually difficult to cut an object at the tips of the scissors, because as the distance from the pivot increases, the force needed to produce the same moment goes down, so that's why the cutting force is smaller. So just to clarify, in any lever, the moment must be conserved. So if you want to increase the force at any part of a lever, you ensure the distance to the pivot is very, very, very small. So the moment throughout a lever is constant, but the closer the lever is to the pivot, the larger the force exerted by the lever to keep the moment the same. And this is what we call a force multiplier, because it changes the size of the force, it multiplies the force to keep the moment constant. Now gears are another example of a force multiplier. They work like levers, but they actually work in a different way, because they don't keep the moment constant. What they do is they keep the force constant. Now gears are simply wheels with teeth around their rims. So in gear systems, the two wheels will rotate in opposite directions. So when one goes clockwise, the other goes anti-clockwise, and vice versa, because the teeth of the gears fit into each other. So as they rotate around an axle, they'll cause them to go in opposite directions. So let's have a look at what's going on. Now, different size gears can be used to change the moment of the force. So in a gear, the moments can actually change. So in a lever, they can't change, but in a gear, they can change. Now, if you look here, look at these two wheels. Now, there's a large wheel and there's a small wheel. Now, because we know that the large wheel has a large distance from the pivot, which is where it's rotating about, the screw at the center, to where the force is applied, the edge where the teeth are, if there's a large distance, well, there's going to be a large moment, because we know that the large distance will lead to a large moment, and conversely, because on that small wheel there's a small distance between the pivot and where the force is exerted, there's a small perpendicular distance, so it's a small moment. Now this is true because they both have the same force exerted on them. Now you might think, well, why do these two wheels have the same force exerted on them? Well, it's something to do with Newton's third law of physics, which states that when two objects are interacting, in this example, two wheels, they will exert equal sized forces on each other in opposite directions. So when these two wheels interlock with each other, they will exert the same force on each other but in opposite directions, which makes sense because it causes the two wheels to rotate in opposite directions. So let's imagine we had an input wheel and an output wheel. They were the same size. So if they have the same size, they've got the same force acting on them, they've got the same perpendicular distance from center to edge, so they must have the same moment, so they will have the same speed because they're the same size, but the only difference will be they'll rotate in opposite directions because that same force is exerted in different directions. So in all gear systems, wheels rotate in opposite directions. But let's look at this scenario. Imagine our input wheel is larger than the output wheel. Well, we know that there's a large distance on the input wheel, but a small distance on the output wheel. Now we know that there must be the same force on each wheel. So the large distance gives a large moment, because moment equals force times by distance, and the small distance gives a small moment. So the smaller wheel will have a smaller moment than the larger wheel, but it's going to rotate faster because it's smaller, so it's easier to rotate. Now let's look at the other way around. Let's look at the input wheel being smaller than the output wheel. Well, the small wheel has a small distance between center and edge, and the output wheel has a large distance between center and edge. So now, if the same force is on each wheel, due to Newton's third law, The small distance gives a small moment. Remember, moment equals force times by perpendicular distance. The large distance gives a large moment. So now the larger wheel will have a larger moment than the smaller wheel, but will rotate slower because it's a bigger object. So it's going to be harder to rotate. So here's an example question you might get. So a gear with the radius of 0.1 meters is turned by a gear with a radius of 0.05 meters. The moment of the smaller gear is 20 Newton meters. Calculate the moment of the larger gear. Well, let's remember what we know. In a gear system, the force must be the same on both wheels. So let's use that as our starting point. So the first step is calculate the force on the teeth of the smaller gear, because we know everything about it to work out its force. So if moment equals force times by distance, well then force equals moment over distance. Pop the numbers in from the question. 20 divided by 0.05 equals 400 newtons. So as a result, if that wheel has 400 newtons exerted on it, well, the second wheel must have 400 newtons exerted on it. And it wants you to work out the moment of the larger gear. So moment equals force times by distance. You know the force, which is the same on both wheels, is 400 newtons, times it by the distance 0.1 equals 40 newton meters. Then the last thing you want to do is do the logic check. Does it make sense? Well, it's a larger wheel, so it's going to have a larger distance with the same force, so it's going to have a larger moment. So therefore, it's double in distance, so it's going to be double in moment, and it is, so it makes sense. Now, the last thing we're going to look at in this revision session is pressure. Now, there are two main types of pressure found in the real world. Solid pressure, which is the pressure exerted when a solid object places a force on a surface, and fluid pressure. Pressure exerted when the particles of a fluid collide with the surface. So a fluid can either be a liquid or a gas, and in these liquids and in these gases, particles have a random motion with a range of speeds. So all the particles are basically moving around. Now as they move around, they will collide with the sides of the container that they are in, or on the surface that they are going to be touching as they move around. Now all sides will have roughly the same amount of collisions because the particles are moving around at random, so they're not going to favour a particular side or surface. So when these particles collide, they will collide and exert a pressure on the surfaces or on the container, so the fluid has created a pressure. Now the pressure will always act outwards because the particles are hitting against the side of it, so it's always going to be pushing outwards. Now, we also know that the pressure will produce a force normal, or in this particular example, 90 degrees to the surface and the containers. So the force is at right angles to the surface the pressure is exerted on. So fluid pressure, which is just the pressure you would find in a liquid or a gas, is the pressure exerted when the particles of a fluid collide with the surface, and it will always cause a force normal or at right angles to any surface that it's in. Now we can work out the pressure with the equation pressure in pascals is equal to force normal to a surface in newtons divided by the area of that surface in meters squared. So the pascal is actually the unit of the force divided by the unit of the area, so it's newtons per meter squared. But say for example the area is millimeters squared or centimeters squared, you then can't use pascals. You've just got to use the notation of the unit of the force divided by the unit of the area. So it could be newtons per centimetre squared, newtons per millimetre squared, newtons per kilometre squared. So you can work it through like that. And you've got to memorise this equation again for your examination. So you are expected also to rearrange this equation and make the area or the force the subject of the equation. So it's a common rearrangement to actually work out the force. So the force normal to a surface is equal to pressure in pascals times by the area of that surface in meters squared. But if you have a change in pressure, you'll produce a change or a resultant force. So you can also write out as a resultant force equals a change in pressure times by the area of the surface. So let's look at an example question. So a gas inside a container applies a force of 400,000 newtons. The walls of the container have an area of 8 meters squared. Calculate the pressure of the gas. We can calculate the pressure with the equation pressure equals force over area. Pop your numbers in. Check how many significant figures. Well, the container area is 2 sig figs, so we'll give it to 2 significant figures because it looks like the force one is to 5 significant figures. So therefore we'll go to the smaller value 2. So it's 5.0 times 10 to the 4. Pop our units in. We'll go to newtons, meters squared. So the units of pressure are therefore the Pascal. Now, in open systems, like an ocean, like a lake, like an open top of a bucket of water, pressure of a fluid increases with depth. So that means that at the top of the liquid, at the top of the fluid, you've got a low pressure. At the bottom of the fluid, you've got a higher pressure. Because as the particles move around, they collide with each other and produce forces at right angles, like we mentioned before. And so there's always going to be a downward force of weight acting down. Now, the further down you go in a fluid, the more particles there are above you at a particular point. So there are more particles exerting a force downwards above you, so that this force will accumulate and add up and add up and add up. So the further down you go, there's more particles above you exerting a weight or force downwards, so the force gets bigger as you go down, the pressure gets bigger as you go down. So there's a low pressure at the top because there's only a few particles above this point pushing down, so the weight pushing down is low, there's a low pressure. But if you go really far down, there's many particles above you pushing down, so the weight pushing down is high, the pressure is high. So the weight of a fluid will increase with increase of depth, and the pressure acting downwards increases with depth. So that's a very, very important idea. So in open systems like oceans, like lakes, that if you go horizontally across, actually there's the same number of particles roughly above that point, so the pressure is actually constant as you go along that particular system horizontally. So when you move along these horizontal lines, you're actually experiencing a constant pressure. And in air, we call out those ideas isobars. So it's important to note that if you go down in these to different depths in a fluid, there's different pressures. So there's a change in pressure as you move from one depth of a liquid to another part of a liquid. And what did we say earlier? We said that if you have a change in pressure, there will be a resultant force exerted. Now, you can either think of it that the change in pressure produces the resultant force, or the resultant force produces the change in pressure. Ultimately, it doesn't matter which way round it is. They're both mutual effects. So, because there's a change in pressure, you've got a force produced by this change in pressure, or vice versa. So therefore, we can calculate this actual size of force by looking at the change in pressure. So we can say that the force produced is equal to the change in pressure times by the area that it's acting upon. So again, it's the same equation as before, so it has to be memorized for your examination. And it calculates the resultant force of the change in pressure. So what have we learned? In an open system, the fluid pressure increases with depth because the further down in the fluid you go, the greater the amount of particles above that point producing the force downwards. But in an open system, the fluid pressure is constant in a horizontal line of the same depth because you get the same number of particles above that point exerting the force downwards. And a difference in pressure can cause a resultant force on an object, which can be calculated with the equation resultant force equals change in pressure times by area. So in terms of the oceans, okay, we're at the top of the ocean to experience a low pressure. If we go down and down and down to the bottom of the ocean, on the ocean floor, you've got a high pressure. And we can calculate the change in pressure in the fluid with another equation. So pressure change is equal to the change in depth you experience times by the density of the liquid times by the strength of gravity. Now, you are given this equation in your exam. You don't need to memorize it, but what you do need to be aware of are what the units are. So you can look at what the units in this equation are, and that can only be used for a fluid in an open system. So you can't use it for a solid. You can't use it if it's a closed system. It's got to be an open system. So it calculates how the pressure changes when an object moves from one point in the fluid to another point in the fluid. But if you just wanted to work out the pressure at a particular depth of a fluid, you can use with the equation pressure equals depth times by density times by strength of gravity. So that calculates the pressure at one particular point of your fluid. So there are some very, very useful fluid equations which you've got to be able to use in your examination. And again, if you sit in the higher tier examination, it really will be expected that you've got to rearrange this equation as well. Because if you're given an equation in an exam, you should be expected to rearrange it if you're doing the higher tier. So let's have a look at a example calculation. So calculate the pressure due to seawater of density 1050 kilograms per meter cubed at a depth of 200 in the sea of 200 meters. So you find your equation, which is written in the equation sheet in your exam. Pressure equals depth times by density times by strength of gravity. So you plug your numbers in. 200 times by 1050 times by 9.8. Always put the numbers in and write it out because it shows you've understood how those values link with each other. So if you make a mistake on your calculator, you'll still get the mark for that. Then you look at how many significant figures, you pop it in, and it's 2.1 times 10 to the 6th. Check the units, it's pascals, and there's your answer. Now we can link the concept of fluid pressure to density and the idea of floating and sinking, because the density of an object determines if an object floats or sinks. If an object is less dense than the liquid it's submerged in, it will float. If it's more dense than the liquid submerged in, it will sink. An object floats if you think in the forces, the force of upthrust, which is acting upwards as the name suggests, equals the force of weight, because the forces on the object in this vertical plane are balanced. So there's no resultant force. It will have a constant motion, which is just a float with no velocity. Now an object will sink if the weight is greater than the upthrust, because the forces now are unbalanced. There's a resultant force downwards, causing it to accelerate downwards. Now this idea of flotation and sinking links to the concept of upthrust. But why do we actually get an upthrust force? Well, when an object's in water or any fluid, that, as we said before, the fluid pressure increases with depth. So if you look at this particular object, there's a higher pressure at the bottom surface of the object compared to the top surface of the object, because it's greater density, it's a greater depth at the bottom compared to the top. So therefore, there's a difference in pressure on the object. So a force will be exerted because there's a difference in pressure, and a resultant force is always produced when there's a change in pressure. So the resultant force will be acting from high pressure to low pressure. That's how forces always act in a situation. It's the same effect that explains the wind. Wind is produced by a force which is exerted on air particles to move from a high pressure to a low pressure. So because in all liquids pressure increases with depth, the further down you go, the more particles are above you pushing downwards. So it produces this difference in pressure, and it produces this upthrust force. So whether an object floats, again, depends on this concept of density and upthrust, because when an object that's less dense than the fluid it's placed in weighs less than the equivalent volume of its fluid, so therefore it displaces a volume that's actually equal to its weight before it's completely submerged, so it's going to float. Now, an object that's denser than the fluid is placed in weighs more than its equivalent volume of fluid. So this means that the object will never be able to displace, to kick out enough fluid to ever equal its weight and to float, so it will sink. So this means the weight is always going to be larger than the upthrust, so it's always going to sink. So like we mentioned before, we can talk about how upthrust is produced. Now the last concept is this idea of atmospheric pressure. So if we live in the atmosphere of Earth, you're constantly surrounded by particles of the air. They're constantly moving about with a random motion with a variety of speeds, because air is a gas, it's a fluid. So there'll be collisions with surfaces which are present in this particular atmosphere. That will exert a force on these particular objects, which will lead to a pressure being exerted, which we call the atmospheric pressure. And the pressure means that the force is exerted, like we said before, at right angles to any surface that the particles hit. Now, atmospheric pressure works in the same way as fluid pressure, because the atmosphere is just another example of a fluid. So firstly, we know that there are many particles above points when you're very low down in the atmosphere, when you're close to the surface of the Earth. So there's a lot of particles above that point, and they're exerting a lot. There's lots of particles exerting a force downwards, so you've got a bigger force downwards, so you get a bigger pressure. The higher up you go, there are less particles above that point, so therefore there's going to be less force exerted downwards as a weight, so the pressure will be smaller. So actually what happens is, the higher up you go in the atmosphere, like in the fluid, there are fewer particles above you exerting a pressure downwards, which gives a low pressure. But if there are many particles above you as you are close to the surface, there'll be many particles exerting force downwards, which gives a high pressure. But there's also a second reason, because as well as that particular idea that the higher up you go in the atmosphere, there's less weight pushing downwards exerting pressure because there's less particles above you, there's also another idea. It's because actually As well, there are fewer air particles in total the higher up you go in the atmosphere. So when you increase your altitude, the air particles are actually further apart. The atmosphere becomes thinner. So as a result, the density of the atmosphere actually decreases with altitude. So there are fewer air particles per cubic meter. So not only the higher up you go are there less air particles above you just due to the fact you're going higher up, but there's also less air particles above you because there's just less air particles in general the higher up you go in the atmosphere. The atmosphere is thinner the higher up you go. So there's two reasons why atmospheric pressure can change: the number of particles present and the amount of force acting downwards. So the closer you are to the surface of the Earth, that means that the pressure is going to be high because there are more particles above you at that particular point exerting a force downwards. But the further away you are from the surface of the Earth, the higher up you are in the atmosphere. Number one, there's less particles above you exerting a force downwards. But number two, there's just less air particles in general, so there's going to be less air particles exerting the force pushing down. So we can link it into that idea. So let's just summarize this idea. Atmospheric pressure is created on the surface by air molecules colliding with the surface. The greater the number of particles above the point in the atmosphere, the greater the weight acting down, the greater the pressure, and there are fewer particles higher in the atmosphere producing pressure as they're further apart from each other, which both links to the idea that as the height or the altitude increase or the depth decreases, the atmospheric pressure decreases. So these are the particular summary slides of what we've learned. So we've learned about, in today's revision session, the determinant effect of a force, linking it into moments, understanding how to calculate a moment, and how you can work out values when objects are balanced. We understand how we can then link this into gears and levers and how they link into transmission of forces and moments where relevant. We can then work out pressure in fluids and the equation to calculate that, whether it be P equals F over A or P equals H times by rho times by G. And then you can understand that differences in pressure at different depths in a liquid, that they occur, and that a partially or totally submerged object experiences a greater pressure on the bottom surface than the top surface, which creates a resultant force upwards, which we call upthrust, which can then link into floating and sinking. And then finally, we can also work out this concept that the atmosphere is a thin layer of air around the Earth, which gets less dense with increasing altitude. And so the air molecules collide with the surface to create atmospheric pressure. And the higher up you go, there's less air molecules above you pushing down and less air molecules in general. So atmospheric pressure decreases with an increase in height. So, hopefully you've enjoyed this revision session looking at moments, levers, gears, and pressure. I hope you understand all these concepts, which are all actually separate science only concepts for the forces module, and have a lovely day.